Welcome to Theorem's Solution channel. Today we are going to talk about Thevenin's theorem. Thevenin's theorem states that a linear two-terminal circuit can be represented by an equivalent circuit consisting of a voltage source V Thevenin in series with a resistor or an impedance R Thevenin or Z Thevenin respectively. So Thevenin's theorem states that a linear two-terminal circuit as such can be represented by an equivalent circuit just consisting of a voltage source like this called V Thevenin and an impedance which can be an impedance Z or a resistor called R Thevenin or Z Thevenin. In this case we'll call it Z Thevenin. So Thevenin equivalent circuit seeks that a circuit, for example a complex circuit as such, can be represented by an equivalent circuit consisting of just a voltage source and an impedance in series with it. So we are going to go straight to the point to analyze this circuit. So we are going to find the Thevenin equivalent of this circuit of figure 1 which we have. So our aim is to reduce this circuit into the simplest form as such, into this simplest form consisting of just V Thevenin and Z Thevenin. So what we are going to do first in this circuit, we are going to convert this circuit into its phasor or frequency domain. So the solution, converting the circuit to its phasor and or frequency domain. Now, looking at this input DC voltage is of the form 6 sine omega t plus some phase difference, say phi. But when you look at this signal, the phase difference phi is equal to 0. So looking at this, comparing this signal with the standard form 6 sine omega t equal to 6 sine 10 t. All of this is in volts. This tells us that omega is equal to 10. So omega, which is a frequency, angular frequency, is equal to 10. So therefore, looking at this, the input signal acting at an angle of 0, just the magnitude, we can consider it to be 6 when we look at this. And next, what we are going to do is to convert this. This is the capacitance, and here this is the inductance of this entire part of the circuit. So we are going to obtain the reactance of this circuit, which is X, the reactance of each component here. So the reactance, the capacitive reactance called XC, is expressed as 1 all over J omega C, where C is the capacitance, and the inductive reactance XL is equal to J omega L. So we are going to substitute these values. From here, from the circuit, we could see that from this circuit, let's calculate XC. XC is equal to 1 over J omega C. And C there, C from this circuit is 1 over 20 farad. So XC is equal to 1 over j omega times 1 over 20. So when you do this, what you are going to have is 1 over j, you know omega to be 10, times 1 over 20. So this one time here 2 times. So you have 1 over j divided by 2, which is equal to 2 all over j. But now we need to express this in the linear form. So we are going to multiply the numerator and the denominator by the denominator using the notion of surd. So xc will be equal to 2j divided by j times j. But you know that j is equals to the square root of -1. Hence, xc is equal to 2j divided by square root of -1 times square root of -1. And this multiplication will give you -1. So 2j divided by -1. So the answer is -j2. I would like to express it in this form, -j2. Okay, so next, xl, which is j omega l, is equals to j times 10 times omega is the inductance here is 1 Henry times 1. So this is j10. So xc is equal to -j2 and xl is equals to j10. So this is what we have. So we are going to convert this entire circuit. We are going to substitute these values we have gotten in this circuit and then analyze the circuit to obtain Thevenin. So I'm going to redraw the circuit. I'm going to redraw it here with the component plus minus 6 at an angle of 0 degrees. I'm taking the magnitude. This is a 4 ohm resistor. This is the voltage controlled voltage source. There is a voltage controlled voltage source. This source is controlled by the voltage V0. So this is a dependent voltage source, a voltage controlled voltage source. And we have the mesh current here, I0. Next, we have the current controlled current source. A current controlled current source. This is a dependent current source which is controlled by a current I0. So whatever value of I0 you put here will change the value of this current. So it's a current controlled current source. Voltage controlled voltage source. Whatever value of the voltage V0 you put, the voltage here will change. Next, you have the capacitance -j2, the reactance -j2, and the inductive reactance J10, and your terminal A, B, V0, positive, negative. So this is a circuit which we are going to analyze meticulously. So next, looking at this, V0, looking at this circuit, V0 is equal to VAB, which will be equal to our Thevenin, which we are looking for. So have this in mind. So first, we are going to analyze this circuit. So we will start by taking KVL at mesh 0, where I0 is. So KVL at mesh 0. current entering KVL at mesh 0, So when you look at this, the current is flowing like this. When you watch my previous video, I meticulously explain how to identify the direction of voltage in each passive circuit component with respect to the current. So this current is flowing in this direction towards the right, so the voltage is acting in the opposite direction. The head is positive, the tail is negative. So we are going to analyze this circuit. So moving from here, we are leaving this source at the positive terminal, so the voltage is positive. So we are going to have 6. Here we are leaving at the negative terminal, the voltage is negative, minus, so it will be minus 4 I naught. And here we are leaving at the negative terminal, the voltage is negative. So you have minus V naught over 3, and we are back here, equal to 0. So we are going to simplify this. Here you have 18 minus 12 I naught minus V naught equal to 0. So when you do this, you have 12 I naught plus V naught equal to 18. So this is our equation 1. Next, we consider the output. When you look at this output, the current this is an entire node, all of this is one node. So when this current enters this node, it's going to split. Part of it will go here, I1, part of it will go here, I2. There's no current flowing here because this is an open circuit. So when you look at KCL at node, let's call this node N. At node N, current entering the node, KCL states that Kirchhoff current law states that the sum of current entering a node equal to the sum of current